National wireless emergencies.
Okay. All right. So, hey, what you're looking at here today, I want to talk about limits some more. Talk about that idea of what a limit is. I kind of went through the example yesterday, but today is to talk about the more practicality of it for the math problems we're going to have. This is your first example. You do not need to draw this in your notes. I would recommend it, but you don't need to because we're going to go through a couple problems, and then we're going to get to why we're doing this stuff. Because that's kind of, in chapter 2, what we're moving toward. Okay, a limit is a theoretical number that your graph or function is representing at that time or place. Okay, some problems have a different complete limit than what the function answer is, and that was the example I gave you yesterday at the very end of class. We're going to talk about that one today. I'm going to bring that problem back up here in a minute after we get through this one. Because this one has a slightly different thing than what we talked about yesterday. Hopefully everyone is comfortable with that limit notation for how they write like this. Everyone knows that says the limit as x approaches 1. And what you're trying to do is figure out where that function is going at 1. And then this is the function. They'll put the formula back here. I'm just putting f of x, but they can put a formula back there. We'll look at one of those later so you can see kind of what we're doing. Now, here's the problem. If you look up here on the board, okay, if you look up on the board, there's some new stuff here. So, if you look up here, what's different about those limits compared to what I gave you yesterday?
Nothing.
Yes.
Plus minus.
The plus minus sign. And notice they're in the back. It's not in the front.
Ooh, that's
it's in the
pretty.
back of the number.
It's like the charging in chemistry.
Are those ions?
Okay? No.
Do you know
But
what
it is,
ion
what it is when you have like a number here, I'm approaching this number, whatever it is. It could be a negative number, it could be a decimal, it could be a 0, it could be infinity, like a direction I want to go. But when they put a sign in the back, like a plus sign, what that is saying is that you're approaching 1
From the right.
from the right. Approaching the number 1 from the right. From the right. Now, here's the reason why that's the case. A plus means you're approaching it from the positive side of the x-axis, like the positive infinity side. If you have a negative
So you're
on
going
that
to the
side,
left.
you're approaching it from the left. The negative infinity side, the negative side of the x-axis going into it. So, this is approach 1 from the left versus approach from the right.
Ooh.
They could have different numbers. They could have different numbers depending on what that limit says. Because maybe your graphs go different directions. And that's what we have to look at. Like this problem has that. I just did a snapshot of this graph here. And then the idea is that if we want to approach the number 1, okay, this problem right here, I want to approach the number 1 from the right and the left. Like when they don't put any sign on it, we're approaching it from both sides. And we have to see, do they both merge to the same number on the graph? So, the number 1 on this graph, as I approach this direction, what is this number approaching? It's approaching 1, right? As I go from, these numbers, and I get closer and closer to 1, this is the answer I'm approaching. But when I approach it from the right side, over here, when I start getting closer and closer to 1, this graph is going down. It's going to a different number completely as I approach from the right and the left.
Incredible.
This problem, if this is how they wrote it, I want to approach 1 and it doesn't specify what side.
It's both sides.
It's both. And if they're not going to the same number, it doesn't have a limit. The limit does not exist. Because they approach different numbers, there's not one answer that the calculator would spit out. One's going to negative infinity, one's going to the positive 1 from 2 different sides. It doesn't have a limit. Okay? Does that make sense as I approach and they don't have the same number? Sure. Okay, now let's go to that picture I showed you yesterday. And I'm going to come back to these graphs we're going to talk about. Okay? Alright, here's the picture that I gave you guys yesterday for that problem right before you were leaving. This is the problem that we had.
I feel like this.
It was something like this. As I approach 0, so this is my function, it's g of theta. As I approached x, theta, I should say theta approaches 0 in the middle from the right and the left side.
1.
So as I'm approaching this from the left and right side, this is the answer I should be coming up with. This limit actually has an answer. I'm getting closer to the number 1 from the left and the right side. So it does have a limit. They're approaching the same number, exact same number, so it has a limit. The problem is, what we didn't talk about yesterday is that the function has a different answer. So this is the limit. It's like what the graph is tending to do as they get closer and closer on the curves. But if I were to type this, like what happens if I were to plug 0 into G without doing a limit, just plug 0 in? What answer is coming out of this thing? Nope. The dot that's filled in. Half. Because at 0 on the x-axis, this is the number that was filled in. That's the answer for the function being evaluated at 0. That's different than a limit. A limit is just you look at the curves and see where the curves are going. But a function evaluation like this is what number comes out of that thing. So that the two numbers could be different. Does that make sense when you evaluate a limit versus when you want to evaluate a function?
I have a question.
Yes.
So, why is it not 1?
Why is it not 1?
Because it's
The
close
limit,
by.
the curves are approaching the number 1. But the actual number that the graph is giving, since this is an open circle, it's whatever was filled in on that graph.
So why doesn't
That's
the
the
line
answer for the
go
function.
through the dot at 1/2?
What?
Why doesn't the graph go through the line at 1/2?
Because the graphs could have different answers. Maybe for some reason at 0, that there's some different price for that particular problem. It's like,
How would you express, like, what would be the equation for that graph?
it would be a piecewise function. It'd be a piecewise, we're going to look at that later, when they have two separate graphs and we're trying to see what happens from the right and left
We
side.
won't look at
Yeah.
that. Oh, I get it.
Okay,
Because the top one doesn't include
exactly. Doesn't
0,
exist.
so
Yeah.
then the bottom
So
one
why
does.
is that the limit?
Okay, the limit is anytime you approach from the right and left and they approach the same number, the limit is whatever the graph is telling you it's approaching as on the curves. The curve is saying you're approaching this number, but it doesn't have to be the realistic number for that problem. So this is the real number for evaluating it, but this is the limit what the graph is going.
Yeah, what is the
There's not
point?
one.
Okay, what?
There's no
Which
point
help
in
you find this.
Okay, so we're going to talk about today, like, why are we finding limits? Like, what's the purpose of doing it today? That's what we're going to look at. Okay, the goal right now is to look at, do we understand the right and left side idea? Because they can approach different numbers. Okay, so let's go through that one example I just had up here a little bit ago. Okay, all right, here we go. Let's get rid of this.
When was the last time you gave it detention?
Gave one today.
Why?
Kid was started. Okay, all right,
That's sad.
All right.
I have detention today for sure.
He
Okay.
doesn't have a bag to carry his
okay,
stuff.
all right.
You erase that green mark.
Right there.
Okay.
Thank you.
All right. Now on this thing, let's say we're gonna be evaluating the function at 2.
All right.
Okay. I want to evaluate, not a limit, but I just want to evaluate it too. What happens?
NA.
NA doesn't exist, right? There's no answer.
CL.
Oh, but it doesn't exist, right?
So
There's no answer.
B and
No solution, right? Because there's an open graph. It's not even included. There's an open circle at 2 on the x-axis. But if I did a limit as
Trusty.
I did a limit as x approaches 2 for my f of x, what number is the graph telling me it's going towards?
1.
One.
Which way?
No, I've made
The left and the right. If they don't put it the plus or minus sign, you're approaching from both ends. I'm going, as I get closer to 2 from each direction, this thing is merging to this answer. Even though that answer doesn't exist, the limit is saying that that's the number we would be eventually going to.
Would it be different if you were just saying something from the right, or no?
No, on this problem it wouldn't. If you're approaching from the right, that's the number it's going towards. You're approaching from the left, that's the number. If it was a piecewise where there's 2 different graphs, they would have different answers.
Oh my gosh, why are there little kids?
So, like for instance, okay, here's a great example.
Little kids.
It was actually a really good question. So,
there's
hold
an
on.
army coming towards
Yeah,
us.
this okay. Alright, let's bring
Mr.
it.
Ward, would you like me to protect you?
So now, okay, let's say we're gonna approach 1 from the right side. 1 from the right. So, 1 on the x-axis going this direction, approaching in towards 1. The function itself, where is it going towards?
Negative infinity.
Negative infinity, right? You would actually say that it's approaching negative infinity, but the limit itself does not exist. DNE, right? The reason why, this is what you say, because infinity is not a number.
Yeah, you can't find.
There's not a limit to that graph, right? That A limit is when you're gonna approach like a maximum or a minimum number.
Oh, that number just keeps going.
Infinity, yeah, this number keeps going, it never stops, right? So,
the
you're
limit
gonna
does
say it's
not
approaching
exist.
negative infinity, but the limit itself doesn't exist. So, either one of these to me makes sense. They kind of go hand in hand. You can say, oh, it's going towards infinity, you're correct, but the limit itself doesn't exist in real life. Because you're going in a direction, it's not an actual number. Okay, but that was a really good question, because we need to see that when you're approaching different numbers. Because now, if I approach from the, if I were to approach this function from the left,
It'd be 1.
yeah, if I approach from the left, I'm hitting the number 1. So that does exist. It's not an infinity, that's a number.
They go there to cancel his device.
What's your favorite food, Mr. Ward?
Okay, now let's keep it to math.
But like that.
No,
is
stop.
not- Is there a limit to how much of it you can eat?
Okay, alright, next one.
What did we even answer on the last one?
For this one,
That's that.
Yeah.
this is 1.
Successful people.
But what you did, like so many different numbers, I don't even know what to write down.
Good job.
You did 1 minus, 1 plus, f of 2.
Yeah, we're
No,
doing
write
that
anything
too.
down.
Okay.
F of 2 is because it's an open circle.
Yeah, f of 2, this is when you're evaluating 2 at the function of 2. That answer didn't exist.
So what is
I
that?
need that.
This is when you evaluate, when they want you to, yeah, that's when you want to like substitute a number in and tell me what answer it actually is on the graph, the real answer on the graph.
4 inches up in here.
As opposed to a limit, where limits are, you follow like the drawing, you follow the curves and see where they're going. Doesn't matter if they're open circles or not, where is that graph kind of going towards? That's what a difference is. So it's realistic number in real life versus theoretically where is that thing heading towards. You do need to know both. So,
That's crap.
okay, but yeah, they're 2 separate problems. All right, let's go to another one here. Okay, all right, next graph here. I like in your notes here, this one right here. I would like you to try a letter A in your notes. So draw the picture, or write down the answer, I should say, for letter A on that graph. So the limit is f of x as x approaches -2. Negative 2 is right here, sorry. They're going by 1, so -1, -2. So I want to know the answer, the limit, as you approach -2.
Wait, is that line continuing or is it done?
This,
No, like the curved line.
right over here. This is discontinuous, it stops, has an open circle, then continues down.
Is it 4?
How about the other one? No, how about one the other
Up
one?
there, it definitely keeps going.
And same with the
This.
bottom? The one
Yeah,
that's-
the bottom keeps going. Unless they had like a dot there, that thing keeps going.
It doesn't exist.
Okay,
It
so
does exist.
limit as the function approaches -2.
Does it exist?
You're doing A.
To what?
We're doing part
That
A.
stands for
Part A.
animal.
Limit as x approaches -2, my function.
Wait, I'm kind of confused a little bit.
I don't know
Could
if
it
it
be negative
exists.
infinity or could it be 3?
What? Why 3?
Is it?
I got it before.
Or no,
What?
or whatever.
No, you've never heard that.
Yeah,
It's
Halloween.
definitely-
And you.
Is it 4 or 3?
Yes, you've never heard.
There is?
It's 3.
I would say
It's,
3.
3? I think, really?
Okay.
grab
Draw a
that
line.
ruler.
Please go draw a line.
No, grab the ruler. No, oh my god, please.
Oh my god.
Okay, here we go.
If it's
We're approaching
over-
2. Hey, what side am I approaching -2 from?
You just see
Oh,
what
that.
it's
Oh,
a
the
graph.
positive and the negative side. So both sides. Then since they didn't have it.
You go up and see what.
All right.
point
So
it's
what you're
at.
doing is here's -2 on the x-axis. You're gonna figure out by going straight up and down
He's going to-
where this thing is gonna go
Oh.
Is it 3?
and where these things
Oh.
are.
Oh, that is
Three.
perfect 3.
So that's kind of the idea where I'm hitting. So your answer for the limit where that graph is approaching -2 from the left and the right on the graph, because again, what this means, approaching -2, is I'm getting closer and closer to -2 on the x-axis. It wants to know the answer up here where the curve is at, where it's approaching. I'm approaching the
Are
number.
you doing B, C, D?
What?
Are you doing B, C, D?
Yes, we'll kind of do those. 'cause
We're doing
the next one. So, okay, question?
I got another bigger.
Okay,
It's
so
5.
okay, letter B. Tell me what do you got for B?
5.
Boy,
7.
5.
cool.
Okay.
It's 7.
Are we sure it's 5?
No, it's
Keep
7.
going. There's
7,
like
thank
20
you.
minutes.
It's 7.
5
Alright.
is the solution.
Oh, never mind.
Come on.
Okay, hey, so let's talk about why it's 7.
Because there's a hole.
Yeah, there's a hole there, but the graph, when they said on letter B that we're approaching 0, we're approaching from the left and the right
Oh,
side.
it's on the line.
So
not
the
actually-
curve is approaching 7, so that's what the limit is. That's what the graph is actually telling me we're approaching. The real evaluation of 0, so if they wrote this for letter B, if that's what they had for letter B, then
Then
yeah,
it's 5.
then you would have been 5. That would have been the 5 answer. Like what the real answer is versus what the graph is kind of pointing towards. Okay? Alright, does that make sense, like the idea of what we're doing here? Does anyone still a little confused here? I'm going to test your knowledge here in a
We
minute.
did an extra one.
Oh yeah, okay, let's do letter C
Oh,
now.
yeah.
Okay, so yeah, this was letter A, that was B.
Never C.
I think it would be 2.
D and E.
Okay, alright.
It's 3 or 2.
C, who wants to attempt C? Okay, Nielsen, what do you got?
D and E.
Say it again.
D and E.
Okay, good. So as we're approaching, as the limit approaches the number 2 for my function,
Is the
Oh,
line
I
still
thought
he's
you were
absolutely right.
D and E.
Yes, and I was like, there's no D or E on there.
No, it doesn't exist, right? Because he's absolutely
The
right.
lines
Because
don't connect.
yeah, as we're approaching from the left and the right side to 2, the number 2 here, these graphs didn't connect. They weren't pointing towards the same number. So that's why the limit doesn't exist. Now, if we were to approach from like just one area, like one side of it, then it would exist. Which would be weird. Because like if I were to say this, I want to approach 2 from the left side.
From the left.
From the left, that's this side. Okay, that's this side right here.
Great.
Yeah, that I'm approaching the number 3.
Good.
So, does that make sense, like, why we actually look at this? Because it does matter the side you look at. Okay, it's the perspective of where you're going and what you have. The idea is like, why would this be different? Like a real life situation here, because these are piecewise. They're broken up into pieces. It'd be like a meter for when you have a parked car. Okay, a meter for a parked car. So let's say after 1 hour, you have 0 for free parking for an hour. But after 1 hour,
Wait, I have a question, real quick question.
yes,
If you did the 2 blocks,
yes,
would it be 2?
it'd be 2. That's the number you're approaching. Even though it's an open circle, that's the number you're approaching. Yeah. So hey, if you didn't hear Jane's question, she had a really good question about what happens if you're approaching 2 from the right. So I'm approaching 2 from the right side, and she's absolutely correct. So her question was, even though that's an open circle, is it still 2? And yes, it is. Because it's telling you that's where the graph's heading as you approach 2 from the right side. So the answer would be 2. Even though it's an open circle, it's still the limit. The valuation there wouldn't be the same number, but that's what the limit's pointing towards from the right side. Yeah, good question. All right, now, hey, getting back to my example here, on a parking garage, right? You have free parking, so this is your price, is the y-axis is your prices, what you're paying. This is your number of hours that you have. So 1 hour you have free parking. Between the first hour and the second hour,
It jumps.
it jumps up to maybe it's like $3. Okay, and so for the next hour you have a $3 charge, and as you go up to the next hour, so let's say you're going up to the third hour, now it's going up by $3 again. The minute it hits there, so maybe this is $6. And the idea is that if you were to look at the limit of the parking garage at any certain hour mark, it wouldn't exist.
Why would 1 hour be 0?
1 hour the first hour is free. After 1 hour of parking, you have to put in, you have to pay. It's like, this is how they do it in like a parking garage where you have to take a ticket when you first drive in.
Yeah.
Because they look at how long you've been there, and after an hour, they start charging
In
you money.
Minneapolis and Ramp B, it says, please press button, please take ticket.
Yeah. So, and that's it.
Minneapolis ramp.
But the limits wouldn't exist unless you're in like the
Yes.
middle.
Oh,
Like
but
if I was doing the
recipient.
limit as, in the hour and a half marker, the limit would be $3 in the middle, approaching from right and left. But the limit,
As soon as you
as we
touch
approach
2
2
hours,
hours,
it just jumps.
yeah, it jumps. So the problem is the limit doesn't exist. The evaluation does. Or if we look at the limit as we approach from right or left separately, but you can definitely see there's jumps in graphs. Those are like realistic examples of why a limit exists. Now, what we're going to use this for in this class is to predict a derivative. Okay, and that's the whole goal of what I wanted to get to yesterday. I want to show you what these limits are, and I'll pull up that one problem I showed you yesterday. How instead of having graphs, how could you do it for a formula instead of looking at a picture? How could you do it?
Did you do D?
Yeah, D as we approach 4. What is that? 8. So we're approaching 8. That's 8. This is 7. That's 8.
How do you know it's equal to
A full month of $50,000.
8? Alright.
Sorry, am I in the wrong spot?
No, I just.
Okay, alright. It's hard to see on that.
And you
Okay.
for free.
So now, let's talk about the idea of what we're going into for calc, right? The whole point of this chapter
Calculus.
is to let's see if I have it here. All right, here's the problem that I want you to look at. Just this graph, okay? It looks like the same graph as yours. It's a very flowing, continuous graph. It has ups and downs to it. But what we're going into is at some point in this picture, and I have it off to the side, it asks what's the slope of each of these coordinates. So the idea is that it's the derivative. Derivative is what the slope is at any certain moment. That's called an average rate of change, or
Differential quotient.
okay, or differential quotient. So here's the idea. What we're going to be going into is called slope, which is, it seems easy enough until you realize that there's two different types of slope.
Slope is pretty.
There's an average slope, and then there's an instantaneous slope.
We know how to do average.
Mr. Ward, what about the slippers?
Okay. Instantaneous slope. Okay. And the idea is that the difference between these two types is doing a limit versus just doing an average. Where the average slope is what you did in Algebra 1. It's doing this. Find m, you subtract the two y numbers, you subtract the two x numbers on the coordinates, and you find an average slope, like where the line is going. That's what you do in Algebra 1, like this. I could find the slope between a and b. If you had these coordinates, you could just subtract the two. That's like an average slope. We're not doing that. What we're going into is what is the exact slope at that exact moment. The instantaneous slope, and that's what a civil engineer would do on a curve. So like when you drive out of Garner, and you're going on that little curve by
Oh, so
Quick
they know how
Star.
fast you can go.
Yeah, that's why they rate that curve at 25 miles an hour. Now I know it's slow, probably no one ever does that, but the idea is that. But
Mr. Ward, are you advocating that?
no, I'm not. But the idea is that what that is they looked at the instantaneous slope for a generic car of a certain size. They have a certain number they go by, and that's the number that they predicted that safely you can control a curve in any weather condition. Now, obviously, ice is a little bit different, but they're saying that on a normal like car weight of a certain size, at 20, 25, this curve you can be able to handle that curve safely. If you were to have like a punctured tire or something, you could safely pull over and not go out of control. I think recently one of the kids said earlier that I think somebody went off the curve. Was it Colt?
He launched his moped off that.
Okay.
He forgot a term.
Yeah, it's not safe. And then the idea is that with the speeds they're recommending, you can stop safely without causing a traffic accident.
Mr. Ward, how fast do you think you could safely go on there?
It depends on the car and depends on your
In
car.
your car?
I'm saying like you want to stick with that recommended speed.
No, how fast do you think you could go without flying off? Yeah, like how fast is the literal
I don't know.
speed you could go?
I'd have to look at the curve and see. I don't even know my car weight. I just don't know.
Can we go out there and do that for class? That'd be cool.
Oh, man.
That'd be way more
That'd be good.
safe.
All right. Okay. All right. But what an instantaneous rate of change is, and I know that Reese, you even said earlier, it was called a differential quotient. But more importantly, it's doing this. It's the differential quotient. So it's the differential quotient when you apply limits to it, like this. At the limit, as h approaches 0, and you had this formula that we did yesterday. This is the generic formula for how you find slope. Instantaneous slope on a curve. It works for any type of thing, not just linear functions, but it works on anything.
So what do I put down for my definition of instantaneous slope?
It is the slope of a curve at that moment in time.
The
And
slope
you
of a
put
curve.
slope of a curve, not a line, but a slope of a curve. which is different. Because slope of lines are easy, just that's an average rate if it's a line. And the reason why they do that is because if I were to zoom in far enough by using this formula, if I were to zoom in far enough and pick numbers that are really close together, x's and y numbers are really close, what happens is that curves, if I show you this, they eventually approach straight lines. So where's my cursor? All right, so if I start zooming in here and I zoom far enough, anything that even curves themselves, even curves themselves, if I were to zoom in far enough, they start to just mimic a straight line. So when you start picking, like points that are closer and closer together, you'll eventually approach a line, and that's what they're saying with this.
So
That
it's
it doesn't matter if it's a curve, as long as you're picking numbers that were within this certain delta band, really close together, and you do a limit right there, it'll eventually give you slope at that exact moment.
So that's like the Earth is flat.
If you think about it,
No,
that's kind of
it
true.
is.
Well,
It's at a curve, but
okay.
it's so close
Actually,
down.
I
and
see what you're
it's
saying.
flat.
Okay, yeah. What she's saying is that,
Oh.
the curve, the Earth itself is a big, sphere-ish kind of object. Well, the idea is that you're right. When you're on Earth itself, we're so small and we're so zoomed in, roads look flat, right? You can't see the curvature of
Okay,
the
I didn't
Earth.
think about that, I don't like that.
Yeah,
Right, that's
because
what I said.
that's-
I'm a
Hey,
scientist.
that's really good.
That's really
One of the things that they always say, if you were to
I'm
like,
okay.
so
That's
if,
what I'm going
hey, so if you were to go like sailing, right, and you're on the ocean, not like a lake, but an ocean, you can actually see the curvature of the Earth on the ocean itself, because eventually you can see the boat start to go on the other side of it.
Like falling off the end of the world. basically.
Yeah, it kind of looks like it, where you're kind of just slowly going up, and the mass goes
Have you
down.
ever been off
Because
the end of the
you're
world?
starting to see that limit where the line, you're starting to see a straight line, but then it's starting to approach that curve because you're starting to zoom
I don't know
out
who has
further.
that good of vision, but.
So,
No,
Not
Mr. Ward actually has
like if you look at
33,000
Yeah.
you can cover.
okay,
I can't see it.
now,
That's a great job.
goal is to show you this part and explain how it works. So,
Mr. Ward.
okay, hold on. Okay, let's go to the problem that I had yesterday on the board.
That was such a good point of view, though. Honestly.
It was.
Why am I not?
All right. I believe this is the problem you had on your little sheet of paper the other day.
Plus 3.
Let me move this over.
I got that problem wrong.
Why? Okay.
Hi.
No, because I'm not an expert, okay?
Hi.
That's why.
Okay. Here's a problem that we had on the board yesterday. If you haven't already, I would like you to write this problem down in your notes, please.
Hey, you wrote it yesterday.
Okay, write down your notes though. All right. Write it down. Okay, what we're gonna do is we're gonna find what they call the instantaneous rate of change. That is your differential quotient, and we're gonna evaluate it at h of 0. So we're basically finding slope on a certain curve, and we can look at the generics of this thing. So here's the idea. When we actually do the limit, you can actually just do your normal math. On the top, you can factor things apart, you can FOIL things together, and then eventually we can evaluate if it doesn't cause a problem. So like on the top, I'm going to FOIL those two parentheses together, which are the 2 plus h's, because again, you're just going to try to simplify. Right now, I can't plug in 0 yet. That's how you evaluate limits, if you just take the numbers that they want you to do and plug it in. I can't do that because I'd have like a very small number over 0. You can't divide by 0. So we have to simplify. So, to actually multiply this together, I get 4 plus 4h plus h squared. That's if I were to FOIL those two parentheses together.
12.
Subtract 12 divided by h, and this is as the limit as h approaches 0. Notice the limit, that limit of h approaches 0 has to stay on the problem the entire time. If it goes away, I count it wrong. So,
why?
next,
The salad comes on the top.
the
and
next,
send it back.
we have to distribute those 3 in, so we have 12
Watch it.
plus 12h plus 3h squared. We're going to subtract 12
The 12's
all over
cancel out.
h, and the limit as h approaches 0 has to be on there.
So if we don't show any work, we don't have to put limit as h approaches 0.
No, you gotta show it. Okay. Now, we'll subtract the 12s, they're gone. That's usually how it works, because I always told you about differential quotient. Usually the things that don't have h's go away. If they don't, we'll have to deal with that.
We'll have to deal with that?
And we'll have to divide both things by h
Hi.
in the end. So here's what we have. We have the limit as h approaches 0, and we divide both things by h, because this is what I have right now. I have 3h squared divided by h. I can divide both items by h. That's called the rule of the law of division. So I can divide both by age, and this is what I have. Alright, when I divide them both by age. You know, the age is simplified,